This is Module 1, Section 18.5, where we're going to talk about the adrenal glands. The adrenal glands have a couple different names. Some people will refer to them as the suprarenal glands. I refer to them as the party hat on the kidneys. As you can see in our image here, they look like a little party hat sitting on top of our kidney. But they're found at the most superior poles of the kidney, and they're considered retroperitoneal, which means that they're behind the peritoneum within the abdominal cavity. We have two different components of the adrenal glands. We have the inner medulla meaning, or helps you remember it, is the middle, and then the outer cortex. So the medulla and the cortex have different embryological origins that gives them specifically different functions. So the medulla is derived from neural crest cells. If you remember from ANP1, neural crest cells are forming all of the ganglia, which ganglia are just a collection of cell bodies outside the central nervous system. And the medulla is responsible mainly for sympathetic responses. It's going to be responsible for secreting epinephrine and norepinephrine in times of need, super stressful situations, really acute stress situations. The cortex, on the other hand, this is derived from mesoderm, and this is going to have specifically three different zones associated with it that we're going to talk about here in a second. So the three zones of the adrenal cortex, the outermost portion of the adrenal gland, is the zona glomerulosa, the zona fasciculata, and the zona reticularis. Now, each of these zones is going to produce a different type of molecule or hormone, if you will. So the zona glomerulosa is going to produce mineralocorticoids, zona fasciculata is going to produce glucocorticoids, and the zona reticularis is going to produce androgens, or what we refer to as sex hormones. And we'll go into how each of these function and play a role in the actual physiology of the body here shortly. But you can tell, and you are going to have to know this histologically, it's kind of hard to see here, but we'll go over it in class, is that you can clearly see different zones within the cortex. And it's probably better shown here where it's actually labeled. You can see the zona glomerulosa, the long zona fasciculata, and then the zona reticularis. And that's going from superficial to deep. So this is the most superficial aspect of the adrenal gland, and we're going deeper and deeper into the adrenal gland before we eventually hit the medulla, what's the middle portion. So talking about different hormones of the adrenal medulla, we talked about how this is just a modified sympathetic ganglion. It was made of the neural crest cells, just like all the other sympathetic ganglion of the body. And they're going to majority secrete neuropeptides. So majority of that's going to be epinephrine, which is about 80%, and norepinephrine, which is about 20%. And these can act on different adrenergic membrane-bound receptors, alpha adrenergic receptors and various subclasses. And this is going to cause a wide variety of changes physiologically. It can cause calcium ion channels to open, the release of calcium from the endoplasmic reticulum. That's going to activate a phospholipase enzymes, opening potassium channels, decreasing our second messenger CEMP, which we talked about in chapter 17. So decreasing our CEMP synthesis for our secondary messenger. It can stimulate the synthesis of things such as prostaglandin. Now, when it acts on beta adrenergic receptors and the various subtypes, this can increase CEMP synthesis. So you can see how that there's an inverse relationship depending on which receptor, which adrenergic receptor these hormones are going to bind with. So now looking at the actions of, or furthermore actions of the adrenal medulla hormones. So secretion of these hormones prepare the body for physical activity. This is no different than what we talked about in ANP1 with our fight and flight. So in our fight, our sympathetic response, we are getting the body ready for increased physical activity. We need to increase the heart rate. We need to increase the blood pressure. We need to increase the breakdown of glycogen or increase the amount of free glucose within the bloodstream to use as energy. So when we're looking at epinephrine, this is going to increase blood levels of the glucose. This is going to stimulate the breakdown of glycogen into glucose in the liver, increase the breakdown of glycogen in muscles so that we have more energy for muscles. We're going to break that glycogen down again into glucose. And then also we're going to break down fats. So if we break down the adipose tissue that we have, this will release fatty acids into the blood, and we can then metabolize those for energy as well. Like we talked about in ANP1, epinephrine, norepinephrine, increase in heart rate, increase in the force of contraction of the heart. This is going to cause the blood vessels to constrict, which will increase blood pressure. This is also going to cause the constriction of blood vessels in areas that are not needed in a time of acute stress or sympathetic stress. So you don't need extreme blood flow going to the gastrointestinal tract. You're not going to be actively digesting anything at this moment. All the other viscera that are not helping, or all the other organs that are not helping in a sympathetic state, what we'll do is we'll constrict the blood vessels away from those organs. It's almost a shunt-like activity, and we're going to focus the blood in areas where you do need tons of nutrients, tons of oxygen, such as muscles, the nervous system, and things of that nature. So we do have a regulation process of these adrenal medulla secretions. So like we had said, anything that's stress, extreme physical activity, even things such as low blood glucose levels can act as a stimulus to the hypothalamus, which will then result in an increased sympathetic nervous system response. So what happens is that we'll have some form of stimulus like we had just talked about. Hypothalamus will then send a signal down to sympathetic nerve fibers. These action potentials in the sympathetic nerve fibers are then going to go and stimulate the adrenal medulla, which will allow it to secrete the hormones of epinephrine and norepinephrine. That epinephrine and norepinephrine will then act on its various target tissues. So, for example, in the liver, we can increase glycogen breakdown and we can increase glucose production. In adipose tissue, we will increase fatty acid release and we will decrease glucose uptake. If we're not uptaking glucose, we're not going to store it in the form of adipose tissue. We don't need to be storing fats. So we want to be breaking down fats so that we have more energy. In terms of the cardiovascular system, we're going to increase heart rate, increase vasoconstriction to the internal organs. In terms of skeletal muscle, we want to increase vasodilation. We want to be getting as much blood and nutrients to those muscles as possible. And we're going to increase cardiac output, which means we're either going to increase the heart rate or the stroke volume, the amount of blood that's being expelled from the heart with each contraction. And then in the skeletal muscle, what we're going to do is we're going to increase glycogen breakdown, like we talked about. We need more glucose going to those skeletal muscles, and we're going to decrease glucose uptake. So we want to be getting glucose into those muscles. We don't want to be storing it in any way. So overall, what that's going to do is that's going to increase the nutrient supply to the muscles. That's going to increase the maintenance of CO2 and the amount of CO2 that we can use to then go through the electron transport chain, go through aerobic respiration. And we're going to increase the glucose supply to the central nervous system. We're only trying to feed, if you will, areas of the body that are necessary during a sympathetic state. And we're trying to decrease the use of glucose and oxygen in areas of the body where it's not needed at that exact time. So talking about hormones of the adrenal cortex now, the mineralocorticoids, which we talked about, are coming from the zona glomerulosa. The main one here is aldosterone. This is what's going to be produced in the largest amounts in this region. And what happens is that in a time of low blood pressure, we are going to secrete aldosterone to bring it up to normal range. And the way that we do that is we're going to increase the rate of sodium reabsorption by the kidneys. So what that means is that we are going to bring majority of the sodium back into the body rather than excreting it as urine. And what that does, if you remember from A&P1, if we bring more salt or sodium, if we bring it back into the body, water follows salt. As that water follows that salt, we will increase our blood volume. By increasing your blood volume, you are therefore increasing your blood pressure. Some other things that aldosterone will do is it will stimulate the excretion of potassium. So we'll put more potassium into the urine, and it's also going to increase the rate of hydrogen excretion into the urine. So there is a possibility that we can get in some acid-base issues here, but we'll talk about that in our hemodynamics chapter, and then again in our renal system chapter. So glucocorticoids coming from the zona fasciculata. Cortisol is the major hormone here. Cortisol is the long-term stress hormone. It's classified as metabolic, developmental, or anti-inflammatory. And if you see someone that has chronic cortisol levels, or if you know someone that has chronic cortisol, high cortisol levels, pay attention. Some of the signs and symptoms will start to fall into place here. But in terms of metabolic responses, what it does is lipid breakdown. It's going to reduce the glucose and the amino acid uptake in the skeletal muscles. It's going to stimulate gluconeogenesis in the liver and increase the breakdown of proteins. It's also going to increase blood glucose levels and glycogen deposits within the cells. So looking at the different responses of cortisol, so developmental responses, this is going to help in the maturation of tissues, development of different receptor molecules within the plasma membrane, and it's a place for epinephrine and norepinephrine to target those individual receptors. Now, the big one here is that chronic high levels of cortisol is actually troublesome because you can have decreased immune response. So cortisol has an anti-inflammatory response, so we're going to try to decrease inflammation, but we're also going to suppress the immune system. Suppressing the immune system over short periods of time is okay, but over a long time, it increases the risk that you would become sick with some form of illness because you have depressed immune response. Now, looking at the regulation of cortisol secretion, so we have corticotropin releasing hormone, CRH, is going to be released from the hypothalamic neurons in a response to either low blood glucose or stress, typically chronic stress. And this is going to happen by way of the hypothalamo-hypophyseal portal system to the anterior pituitary, because this is an anterior pituitary hormone. In the anterior pituitary, CRH is then going to bind and stimulate cells that are going to secrete adrenocorticotropic hormone, or what we'll refer to as ACTH. So ACTH will then stimulate the secretion of cortisol from the adrenal cortex. That will then be put into the bloodstream. It will then take the bloodstream highway to all the individual target organs. Cortisol is then going to stimulate these target tissues. And then cortisol will act on target tissues, like we said, to increase lipid and protein breakdown, increase blood glucose, and increase anti-inflammatory properties and depressant of the immune system. Just like all the other anterior pituitary hormones, it does have a negative feedback loop where you can see that we can inhibit CRH and ACTH, either CRH from the hypothalamus or ACTH from the anterior pituitary, to act in our negative feedback loop to then stop the release of cortisol from the adrenal gland. Now, talking about adrenal androgens, or what we'll refer to as sex hormones, this is going to happen in the zona reticularis. And what these are different weak androgens that are going to be secreted and converted to testosterone in peripheral tissues. This is really what's starting to regulate and create your secondary sex characteristics, pubic hair, axillary hair. This will increase sex drive in females. This is what's really forming your secondary sex characteristics is the adrenal androgens from the zona reticularis of the adrenal cortex. So here's some different symptoms of hyposecretion and hypersecretion of the adrenal cortex hormones. I would pause the video here and review this. We are going to review this intensely in class. These are very common to have hypo or hypersecretion of adrenal cortex hormones. So we're going to go through many examples in groups to kind of further understand these processes and what's going wrong. So pause the video here, read through this, and have a general idea before you come to class.